AP Review Session, Lesson 6. In this lesson we'll take a look at some free response questions dealing with gases. In the previous lesson we looked at the same concerning, we looked at some multiple choice questions. So to begin with, we have, it says samples of carbon monoxide and CO2, carbon dioxide, are placed in 1 liter containers, as in the diagram on the left. Now this is a bit hard to read, and this says on the left side we have carbon monoxide, CO, on the right side we have CO2. CO is at 2 atmospheres, CO2 is at 1 atmospheres, and both gases are at 25 degrees Celsius. Okay, so this is going to be more of a qualitative type question with some explanation. A says indicate whether the average kinetic energy of CO2 is greater than, equal to, or less than the average kinetic energy of CO molecules, and then justify your answer. So here justifying will be very important. Now, kinetic energy is actually measured by temperature, and because temperature is the same in both cases, the kinetic energy is actually equal in both cases. So Ka is equal because the temperature is the same. And we could say temperature is a measure of the kinetic energy of molecules. That's the idea. As long as we're at the same temperature, the amount of kinetic energy is the same. Now, question B, question B goes a little deeper into this idea, and it says, indicate whether the root mean square speed of the CO2 molecule is greater than, equal to, or less than the root mean squared of CO molecules. Again, justifying the answer. Now, the root mean square speed, just ignore the root mean square word and just think of the speed. So it's asking which molecules are traveling faster. Now, kinetic energy is the same, but if you recall, kinetic energy from physics and from our chapter 10 is 1/2 mv squared. This is the equation used for moving objects, and because particles are moving objects, we can use this. So the idea of root mean squared, the square, comes from this 1/2 mv squared. So the m, remember, is mass, the v is velocity. So this is an inverse relationship, meaning that the heavier the particle, the higher the mass, and the lower must be the velocity in order for it to still have the same kinetic energy. So in fact, the heavier molecule, CO2, travels slower. CO2 speed is slower because it is more massive. So the kinetic energies are the same because we're under the same temperature, but the speeds are not, is the idea. And then C says indicate whether the number of CO2 molecules is greater, less than, or equal to. Again, justifying the answer. Now this comes from the fact that the pressures are different. So notice that our volumes are the same, our temperatures are the same, but the pressures are different. And the only way you can have a higher pressure in the CO compartment or container is if you have literally more molecules of CO. And if you plug both of them into PV RRT, you'll find that the moles of CO is greater. So CO is greater because the pressure in the carbon monoxide container is higher under the same conditions. And that's the idea. So a qualitative type question that tries to get at some of the details of gases. Let's go ahead and finish up with a quantitative question, one that's related to lab. This one's going to be a little in-depth, so let's make sure we can do this. So the equation above represents the decomposition of a compound containing an unknown element, X, and we have a mass of the compound, 1.39 grams, that's decomposed completely by heating. So all of it will become gas. Notice our gas is the oxygen gas. The gas produced by the reaction was captured over water. This will be important. In a gas collection tube at 24 degrees Celsius. The total volume of the gas is 506 milliliters, and the total pressure inside the tube was determined to be 739.5 torricellis. The vapor pressure of water is 22.4 torr at this temperature that we're working at. Now remember, anytime we collect gas over water, so if we have water and we want to collect, we have a tube here, and we're which has a bunch of water in there, and we want to collect the gas. This is also water. We want to collect the gas in the tube. Part of the pressure inside this tube is going to be due to the water vapor, because under any conditions water actually evaporates. So what we'll have to consider, that's where this torricelli comes in. This is just due to the water vapor when the water evaporates, essentially. So initially, part A says calculate the partial pressure of just the oxygen that was collected. And the idea here is that in the same volume, your pressures of the different gases add up together. So all we have to do is just subtract the pressure of the water from the pressure of the total. So the total pressure is 739.5 torr minus 22.4 torricellis. We should get something like 720, what is that? Or, I'm sorry, 17.1 torricellis. And again, you can use the calculator on this free response portion. So this would be the pressure of the O2 gas. So this one is pretty simple. And now they want to know the number of moles of oxygen collected. So this, we just apply PV equals nRT. And we want to know the moles, so we want to do N equals PV over RT. Now R is going to be provided for you in the packet, in the whole packet, so you'll know R to be 0.0821 liters, atmospheres, moles, Kelvin. So in our case, now the pressure, because R is defined in terms of atmospheres, we have to get the pressure into atmospheres. And if you remember, this will also be given to you. 760 torricellis are equal to 1 atmosphere. So you would convert between these two units. So we end up doing 717.1 over 760. And go ahead and use your calculator to figure this out. And this should give us 0.943 atmospheres, ATM. So our pressure will be 0.943. Our volume is given to us as 506 milliliters. So in liters, 0.506. We have to do it in liters because, again, R is defined in liters. R is a constant, 0.0821. And then temperature in our case is 24 degrees Celsius. Add 273 to this, and we should get ourselves 297. So we get 297 Kelvin. So plugging and chugging, we should get, if you plug these numbers in, again, you have the calculator at your disposal, and you should come up with a value that looks like this, 0.0196 moles. You can go ahead and verify that. This would be moles of oxygen gas. So notice we used PV and RT to determine the moles of oxygen produced. On the next page we have a few more questions regarding this example. C says determine the number of moles of the chlorate that was decomposed. So here it's a stoichiometry problem. Since we know we have from the previous slide 0.0196 moles of oxygen, simple stoichiometry, we'll go from moles of oxygen to moles of XClO3, and it's 3 seconds to 1. That's a bit strange. The fraction of oxygen is 3 seconds, but you can easily put 3 seconds down here, to every 1. We're just doing the same thing we did before. And then if you multiply this out, you should get yourself 0.01305 moles of XClO3. So a quick little stoichiometry problem. D says determine the molar mass of the compound. Now the molar mass, they actually gave us this mass to begin with. Since we know grams, we now know moles. We now know moles. Molar mass is grams per moles. So take your grams and divide it by your moles. So we have 1.39 grams divided by our moles, which is this number, by 0.01305, and we should come out with 106.5 grams per mole. Now, the AP exam does take a look at significant figures, and they usually give you one significant figure either way. In all three of these cases, we have 3 sig figs, so we should really say 107 grams per mole. Now, if you said 106.5, you would have been given it because you're within one significant figure, but this should do it. Then finally, we're asked for the identity of the element X. Since X is an element, and it looks like it's going to be a metal because chlorate is a polyatomic ion. It looks like it's going to be a group 1 metal, so like potassium or sodium, something like this. But the way we can find out is we can simply subtract away from 107, subtract away the mass of the ClO3. And ClO3, we have 3 oxygens. Each oxygen is 16, so 16 times 3 plus each chlorine is about 35.45. So just to subtract this whole thing. So we end up doing 107 minus, that's 48, and 35, 45. That's 83.45. Again, you could use the your calculator, so this shouldn't be too bad. And we get roughly 23 grams for the element. And if you find sodium, good old sodium, element number 11 is 23 point something. Probably, I think it's actually 22.99 grams from the periodic table. So sodium is the culprit. So this was using PVNRT and using some other concepts. Very often the AP exam loves to combine questions, lab type questions, with one of these concepts. So this should conclude for us the lesson. I'm going to go ahead and cycle through the rest of the questions just in case you can't pick them up from Edmodo. So just kind of pause and take a picture or copy them down or anything you like. So here are some homework practice problems. We'll cycle through the multiple choice first. (11), 12, 3 parts here for your educational pleasure. We got 13, we have 14. Do we have 15? We certainly do. And 16? Nice. Don't stop now. We're on a roll. 18. Still multiple choice. So you should be excited about all this opportunity. 19 then is a free response and be able to do some free response style questions. Here's 20 with some more parts. And then finally 21. I think this is the very last question. So hopefully you'll be able to obtain the notes. If not, go ahead and take them from here and enjoy.